right. All right, we're back onto linked lists today. We got a little bit ahead, which is good, of the plan. So we'll have more time to work on linked lists today. And then on Wednesday, we'll finish them up and be able to talk about the project. Then I do want to talk about the third project. I don't want you to spend a lot of time over the midterm on it, but the midterm won't be too bad. So I'd like it to be done this week so you have time for the group project. If it needs to take a little longer, like I'm open to that being turned in maybe the 14th. But really we want to get the focus on the group project so you've got the whole month to work on it. It's sort of the idea there. Just want to make sure you get enough time for that one. That's the important one. Not that these other ones aren't important, but that's like kind of everything at the end. So, wow, week 9. That is crazy. It is almost November, which is cool. It's almost election day, so do check out. I think the university's probably sent you a bunch of stuff. I get a bunch of stuff. If you haven't gotten stuff about voting, I'm probably going to spam the Discord later. So you're probably tired of it by now, and I apologize, but it is important. So do take a couple minutes and check that out if you get a chance. All right. So before we jump back into the code, I want to take a look at our drawings again. Excuse me. So we left off with a couple things to do here, and then we had our linked lists. So far what we had done is we had a node here, right, with some kind of data and some way to point to the next node. And what our linked list class had was it knew where the first node was. Right? So linked list knows where first is. So we can always track where the first node is, and then from there we can follow these links and say, okay, where's the next node? Right? Where's the next node? Where's the next node? So on and so on and so on. But when we go and add stuff to a linked list, then we're sort of adding it in reverse. Doesn't really feel like a list usually is. Like if you're making a list, usually when you add stuff to a list, you add it to the end of your list, right? And when we've worked with vectors, when you push back on a vector, it adds to the end of the vector, end of the list. So can you think of a way that we could add stuff to the end of our list without having to take n operations to go, okay, here's the first, here's the second, here's the third, here, on and on and on and on. How could we get right to the end there? Can we think of a way? Well, how do we know where the start of the list was? What do we have that tells us where the start of the list is? You have this pointer, right? So we always know where the start is. So we said, hey, anytime we want to add a node, we'll just add it. It becomes the new first to get that constant time operations. Could we do something similar with the last pointer? If we know where the last node is, could we add something right at the end? Right? Because last not next should be this null thing here, right? It doesn't have one. So if we wanted to add a node at the end of our list, all we have to do is make a new node. Not the right click, right? Make a new node, put our data in here, and say, hey, last, your next isn't null anymore, right? Get rid of that null. You now point to this node over here. And then, by the way, last, now you're this thing. We have a new last. And then how many operations is that going to take in terms of how many n items I have? It's constant, right? I could have a gazillion items here. I still add a node, tell the current last its next is now this, and then move last. It's the same number of operations, no matter how many it is. So even in our worst case performance, which I know I said we don't generally care too much about, worst case is important to know. Like that one is important, but we don't always talk about it as much. But the worst case for an array-based storage, a vector kind of storage, was it took n operations, right? Because I had to double my size to make room for the next spot and copy everything over. And we just said, well, really, it averages out okay, which is true. But the worst case means it is really slow. With a linked list, the worst case is never slow, right? This big O is always constant for worst case, average case, and best case, right? So we've improved on the performance of adding something. Now we get a worst case of still constant, which is good. Now, the thing we kind of skipped over here, remember when we talked about this big O notation and complexity of algorithms? We said you care about time performance and you care about space performance, how much memory we're using. What do you think uses up more memory? Storing nodes with addresses and pointers, or storing just one big chunk in memory here with a vector? Like, let's store a bunch of things. 1, 2, 3, 4 versus 1, 2, 3, and 4. Which one is going to take up more memory, more space? The linked lists, yeah, because we have to manage nodes, we have to manage these next pointers. And by the way, in like a 64-bit memory system, like when our computers are 64-bit systems nowadays, like pointers are 64-bit items. They're not small, right? Like if you think of, you can store a double in how many bytes? 8 bytes for a double, I wanted to say. That's not right, because it's 4 bytes for an int. I should really remember these things, but I don't. It's like not that important. You can just go look it up. But 64 bits is 8 bytes. So every pointer here is another 8 bytes that we're storing. So like we're using a lot more memory here. But we're getting a performance trade-off here. So when we're looking at what is a good solution here to use, what's a good tool to solve our problem here, it's a trade-off. We're going to use a little bit more space, like twice as much space, depending on what else we're storing in here, right? It's, versus getting better performance. Okay, so in our linked list class then, put this down, it's awkward to hold. Our singly linked list here. Now, I mean, we left the destructor, copy assignment operator, copy constructor. We'll get to those. We've done them. I feel like it's not as important to go over and spend a bunch of time on. Is that wrong? Is that a bad assumption? Because anytime we're allocating new memory, we should have them. So we're saying we should do these things, but we'll get to it later, right? All right. So if we also then keep a node of type T pointer for the last, we can start adding to the end. So this add here, we want to say add maybe to the front. It's probably a more proper way to reference this then, because we're adding to the front here. Now, when we add to the front, now we have special handling that has to happen. So now that we have a first and a last, it gets a little weird because we have two cases, right? The first case is the list is empty. They're both null, right? The other case is they're not null. I have stuff in the list, right? But two different things happen because if we said, hey, I want to add to the back, take the last nodes next. If last node is null and you try and set the next on a null, it's going to crash on you. We'll get a null pointer exception, right? So trying to add something if it doesn't exist is trouble. So we have to add a little extra special handling here. So where our first addition here was pretty easy because if first was null, our next is null. That's easy. There's no special handling here because it accepts whether or not first is null or not. That just becomes our next thing. But you can't set the next value of null, right? If we're gonna add to the last. So then the other thing we need to do is when we're adding to the front, when we're empty, we also need to go set last, right? So if our number of items is 0, if we were currently empty, right, our last then equals the new node because we had no items. So if I'm going to add something to the front and I have no items at all, well, the only one item in there is the first and the last, right? So we're saying, hey, if I had no items, this was the very first thing, essentially, right? This must be the first item was empty before, right? Now we have a last, okay? And last will just stay here, right? Last isn't going to change when we add the front here. It will stay as the very first thing we added. I don't have chat open here. Oh my goodness. Hopefully you guys aren't chatting at me. But I heard some notification. Oh, hey, thanks for coming in, folks. Good to see you. We've got some friends. Yeah, I just opened up chat. Thank you, though. So adding to the front's not going to change our last. No biggie here. Now, if we wanted to add to the back here, we can add another method. Add to the back a t data here. Going to be very similar, where we're going to take a new node here, but its next will be null for that new node, because this is going to be the last node, so it has nothing that comes after it. So we'll take the data, we'll add it here. Then we need to take the current last and set it, but only if we have a last. We're still doing singly linked lists, DZE. So we can check, hey, if my last is equal to a null pointer, then we have some special handling. And really, the easy way for us to do this and not have to repeat code and not feel bad about ourselves, right? If the last is null, we're empty. I just want to add to the front because it already does all this, right? If we're empty, adding to the front, adding to the back doesn't matter, and my add to the front already works if we're empty, right? So we can take a shortcut here. I don't need to redo this. We can just add to the front the data. Otherwise, we can go do some stuff, right? Does that make sense as a little shortcut here, right? Do more work. Need to. It's already solved, and we can set this. So if we do have a last, though, right, then I can make my new node. I can take my last and say, hey, last's next. You're now the new node, right? Hook it into the list here. Say the thing that was last, right? You used to be last. Now you point over here. You have a next, right? And then we move next, or move last. So then last will equal the new node. And then take our number of items plus plus. Right? So we have our special handling. If we're empty, just go do the other thing. It's already solved. Right? I don't want to add special handling again. Otherwise, add to the end. You guys don't look so sure. That's okay. That's okay. This is new. Hey, thanks so much for coming along, D Chateau. What's not doesn't just doesn't feel good? It's okay. It's gonna get crazier. I'm laughing because it's fun, maybe? I think it's fun. I'm a little weird, but you guys knew that. So now we can add to the front, we can add to the back. We can get something at a given index, sure. Now, if you wanted to make this ever so slightly faster, because some people think that's really cool, if the index is our last item, we could jump right to last. Right? If you have 5 items and you want the 4th index, I can just give you last, the data at the last node. Right? So I can improve performance ever so slightly with the index now that I have a last, right? Because I don't have to count all the way to the last thing if you want the very last thing. Now, if you want one before the last, you're screwed. You still have to count from the beginning, right? Because we have to get there. You okay so far? All right. So this is the singly linked list, where we have one link between our nodes. There's another one you can do, which is really fun. I'm going to add a new class here called a doubly linked list. And these ones are my favorite. We'll change this up in a second. Doubly linked. Okay. The idea with a doubly linked list here is my node now has 2 links. I'm going to store some kind of data here, right? My T data here. I know what comes before me, and I know what comes after me. We'll have 2 links. So every node, you can go either direction, forward or backwards, on a given node. So to do that, right, our node class needs to change. We're going to have a node pointer of the previous. And then again, we'll probably assume that's node t pointer previous is a null pointer until you tell me otherwise. So this previous is the previous. But if you know what it is, cool, we can take it. Yeah. I'm sorry? Oh, I made a CPP. Why did I do that? That was wrong. Thank you. Look at that. It's an H file now. Thank you. Good catch. That would get confusing later, trying to include stuff. Excuse me. Okay, so our nodes now have next and previouses. Now, this doesn't seem like it's all that useful for us, but we'll get to why it's useful in just a minute. Let's set this up first, and then we'll look at why this is super cool. Is that okay? All right, so to make a new first node, right? First is the next value. It has no previous. So the first node should have nothing comes before it, nothing that comes before it, and the last node should have nothing that comes after it, right, with these links here. So easy for what's first, right? If it's the only node, sure, that works fine. It's null and null. We're okay, I think. But when we add to the last item here, we know we have no next, right? Because we want to be the new last item. Our next should be a null pointer. But what comes before the new last thing? Right? If I'm going to add a new last node here, what comes before this one? What was currently last, right? So the previous for this one is the last, right? And then I'll set the last next to the new node, set last to the new node, increase my number of items. So my next is null, but my previous is the last thing. I think we're in pretty good shape here. Now we can actually optimize this ever so slightly. Again, in terms of n operations, we're not really changing it here because any index, on average will be somewhere around the middle. We throw away our coefficients, so we don't care that it's in the middle. Here, it's still n items. But, it still takes time to do things. So if we're closer to the end index, we can start at the last and work our way backwards. If we're closer to the front index, we can start at the front and work our way forwards. Right? So you could add some optimization here, doing it that way if you wanted. So we could say, okay, how about, do you want to write it out or just skip it? Is it enough to say we could do it? Okay, so we could check index is closer to the back half and start at last, working backwards. Right, maybe that's a to-do. Right, we could do that later. Okay. To still get index of to find a particular piece of data is perfectly fine. Now, we haven't really gained much in performance doing it this way, but what we can do now is if I have a linked list here, so let's throw in some data in here and try and sketch this out. So I've got a bunch of nodes out here, right? And maybe a 1, and usually we draw these pointing to each other. So we'll say that's maybe a 2, and then we'll draw another one of these, like a 3. So these all point to each other, and on and on and on. Maybe that one's null. So inserting at a particular index is still slow because we have to get to that index. But what we can do is, if I have a large linked list, I can give someone a position and say, hey, this is where you currently are. If I give someone a position, once you have a position, inserting before and after that is constant. Right? So if I want to put something between 1 and 2, I would make a new node, right? 1.5, sure. And then I would put it in between them. So its next and previouses are here. And then I would break these links here and repoint them all. Now we've added something in constant time in the middle of a list. If you think back to our arrays, right, the array-based storage, to put something in the middle, you had to bump n items down, or k minus n minus k, or whatever worked out, like minus the index, but essentially n items down, right? So to say, hey, I want it to be the new index 2, I had to shift everything down to make room for it. With the linked lists, once you have a position, and this is a little bit of a big once you have one, because it still takes you n operations to get to a position. But once you have a position, you can insert before and after it in constant time. So depending on what we're doing with our list here, this can be really fast for modifying the order of data, right? And then, hey, I've got this position, and then maybe I'll come over here and I'll do something with it over here. So giving someone a position that they save as their own pointer. Hey, where am I currently pointed? Well, I'm pointed at this position. Now I can add before this position or add after this position is really, really, really fast and powerful. But we don't have to do any of that resizing. We don't have to do any of the shifting. We just put stuff in. So if I want to add something at a given index, right? Let's start it here. So we won't do the position version up here, but let's say we want to add a t data at an int. Back to my friend. Thanks for donating those bits to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. You're a legend. So add some particular, and this should be probably void. To add a particular data at a given index, right? Well, we have to get to that index, and we're going to hold on that positional thought for a minute. Just get to the index and put it in. We have to be able to do this first. So similar idea, right? We're going to walk. We're going to start where we are and get to that location. Right? Start at current index, start at the first thing. As long as we're not a null pointer, and my data is, oh, that's not the one we want. I wanted this one, current index. I copied the wrong one, friends. There. Right? As long as we haven't gotten to the index, right? We'll just keep on going. Okay, here's the next one, 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 here's the next one. So once I get there, what am I going to do? So if we have 1, 1.5, 2, and 3, right? This is index 0, this is index 1, this is index 2, and this is index 3. Look at that, it worked out nice. So what index do you want to insert at? Index 1, so we want it to become the new index 1. Okay, so we're going to start and say, okay, we're at 0, we're not there yet. Okay, we'll go to the next node. So current node is this one. So to become the new index 1, are we going to go on this side of it over here, or on this side of it over here? To the left or to the right? If we want to become the new index 1. The left. Yeah, we need to come over here, right? So then it's 0, 1, and this will be 2, 3, and 4. Right? So to move, to put ourselves in between those ones, right? Current node needs to come after me, so I can make a node, right? I'm going to make a new node, given the data. What comes after is the current node, right? So the current node will come after me. What comes before me? How do I get at the thing that comes before the current node? Previous. Current nodes previous, right? So current nodes previous, right? So now I've put myself in the list here. So we have a new node here. My next is correct. My previous is correct. What else do I have to fix? Right? I have to fix these ones here. I have to make sure these ones go away and they point to me. Right? So this gets a little silly looking, but it's okay, I promise. Not the worst thing in the world. It's a little terrible, I'll be honest, but we'll follow here. So my new nodes, previous, next is the new node. Right? The thing that comes before me, hey, the thing that comes after you is me. Right? Go to the thing that's before me, say what comes after you is me. So my previous next is now me. We're breaking that link. I told you it's a little weird. We'll get there. So now, same thing, but in the other direction. My next previous is now me, right? Hey, thing that comes after me, what comes before you is me. Put me in the list. Put me in, coach. Put me in, right? Make sure we don't get jumped over. I don't know how to write this in a comment to make this more clear without it being gibberish. Is there something I can put here? To the node before you, or the new node. It's next to the new node. Is that useful? I'm happy to put these in here because, okay, maybe it's useful. It's not hurting anything at least, right? So go to the node after the new node, that it's previous to the new node, right? So this puts it in the middle and then it makes the things before and after it point to it, puts it in the loop. So we can add something at a given index here. Again, it will take n operations or so to get to this index. This is the slow part. So in terms of performance now, we talked about the positions, I got excited here, but with this adding versus adding to a vector, they're both O of n, right? It takes n to get to an index, and then it's constant to add, or it takes constant to get to the index and then n to bump to make room in the vector, right? So they're both slow. So once we start adding that position stuff, then we can increase our performance with a linked list, with a positional linked list. Okay, but we're getting there. Okay, how would I remove something at a given index? Same idea, but in kind of in reverse here, right? So if I wanted to get a t remove, I don't know what, add an int index, right? Give me the t value at a given index and take it out of the list, right? Or pop, is it pop in vector? I really should remember this. Is it pop? I'm sorry? Pop back. Should we call it pop back? That just doesn't mean anything to me. I like remove. Okay. We'll say pop back in vector. Okay. So I have to get to the index, right? So again, we're going to walk. And hopefully you had a chance to do some of this in the lab, this idea of walking, right? Taking the current node, going to the current nodes next, going to the current nodes next, going to the current nodes next, going to the current nodes next. We talked about doing this walking here on Wednesday. And then I threw the lab at Mr. D. He's like, oh, that sounds like fun. And I don't know if it was actually fun or not. No comment?
No.
I'm sorry?
No, we didn't.
You didn't, like, well, you printed a list, right? Yeah, so to print the list, you had to start at the first one and then print it, go to the next one, print it, go to the next one, print it, go to the next one, print it. You had to walk it, right?
I just did the loop
What did you loop? Like, how'd you get from node to node to node?
using like the index of that node.
Oh, okay, so you just used our, okay, so you could totally do that. Performance would be, oh man, I'm bad at math. So 1 plus 2 plus 3 plus 4 plus 5 plus 6, like every step of the way you're doing that k. What is that? So that's n squared at that point, right? Because so how many operations? Okay, hang on. I know the math to this. This is not exciting at all, right? So if you said, hey, print the thing at 0th index, at 1 index, at 2 index, at 3 index, at 4 index, on and on and on and on in that loop, it would work. But operations you've done is 0 operations, 1 operations, 2 operations, 3 operations, 4 operations, right? So to get the sum of, oh man, what's that value of what, from 1 to n, right? And you're summing n is n times n minus 1, right? This is calculus, isn't it? Don't you talk about this in series and sequences? It's like the whole reason we take calculus in computer science is the series and sequences chapter, I swear. It's like the only interesting stuff, right? So n times n minus 1 is essentially n squared with a bunch of other stuff. We don't care about the other stuff, right? So, n, minus an n or something, right? We throw away the little things when we talk about performance, right? The thing that matters most is your largest exponent when we talk about performance. right? So that's an n squared operation. That's really bad, right? You can do it in n just by walking. Start at the first one, print it, go to the next one, print it, go to the next one, print it, with the same walk here, right? Start at the first node, and really we just go until you hit the end. So I think we did this, like, as long as we haven't hit null pointer, just keep on going. Print it, print it, print it, print it, print it, print it. So this is the more efficient way. Yours totally works. I don't mean to throw you under the bus or anything. I'm sorry. Appreciate you volunteering that. Works, but this performs better. So when you talk about the science of computer science, that's the thing people like to argue about, is what performs better. That's the science-y part of things. Like, how do you take a big problem and break it down and solve it? That's the art side of things, because that's problem solving, and everyone does it differently. Okay. All right. So to remove something at a given index, we have to get to that index. So again, we'll just do our little walking thing here. Right. So get to the current node. So when this is done, we'll be at the current node. Now, we're going to run into some funny cases here, and this is why double linked lists are a little weird. So if I want to remove the very first thing, right, I'm going to have a problem because I don't have a previous. Or if I want to remove the very last thing, I don't have a next. So this will crash without some special handling. So we'll get to that in a second. So to do special handling for first and last. But aside from that, assuming we're somewhere in the middle, right, to take a node out, right, I'm going to have a T for the data is going to be my current node's data. The reason I want this is because I want to hang on to it for a second, because I'm going to get rid of this current node. Right, we need to go delete it when we're done. So we got to hang on to it for a minute. Okay. Then to take something out of a list here, right? How would I take something? Let's say we wanted to take this 2 out of the list here. What do we have to do so it's no longer in the linked chain? Like, how do we get it skipped over? Well, we go to its previous and say, hey, don't point to me anymore, right? Pretend like I'm not here. Point to my next. And then we go to my next and say, hey, don't point to me anymore. I don't come before you. This thing comes before you. Right? So again, some of that crazy notation. So we're going to say the current nodes previous, I can't even talk, friends, next value. So the thing that comes before me, change what comes after you. Don't come after me now. You now point to my next thing. Right? Make the previous node jump over the current node. Does jump over make sense? Right? Point to my next. Take me out of the loop. And then we'll go to my current nodes next and say, hey, your previous value is my previous value. And then this is so making the next node jump over the current node. Takes it out of the loop, out of the links, right? It's no longer there. Okay. Then we can delete the current node pointer. And then we can return the data. Because we've allocated these with all this new notation to make sure we're cleaning up after ourselves when we take out nodes. We've never removed a node before. And this is the first time we've removed a node. Right? Okay. Now, the special handling, though. If we want first and we want last, right? If I'm first, if I try and set previous anything, I don't know why I'm throwing a T in there. Previous is anything, it's going to crash because it's a null pointer. It doesn't exist. Right? If I'm trying to set lasts next, it doesn't exist. It's a null pointer. It's no good here. So we have some fixing to do. And this gets messy, and that's okay. Let's see. I think I don't want to reinvent the wheel here. So we'll come back to this here in a second. Right? We have this to do. Let's add a T move front here. And we'll add a T remove back. So if you want to take from the back or take from the front, let's add those. And in here, we can do the special handling and say, hey, if we're the front, remove the front. For the back, remove the back. Oh, and the other thing we were supposed to do here is take our number of items. Minus, minus, right? Don't forget to take your item count down by 1, because that'd be bad. Okay, so if we're the first or if we're the last, we can go do this here. So let's just jump right to that here. So this will be our special handling, and we'll take care of it. So if index is equal to 0, we'll just call we're going to return remove front. Right? If you want to take out the first thing, just remove the front thing. I'll figure out how to do that in a minute here, but that'll be my special handling. Right? Else if my index is equal to my number of items minus 1, right? Because that's my last node here. Then we're going to return remove back. We call it back? Yeah, remove back. Okay. If it's not one of those things, let's keep on going. Then we know it's in the middle somewhere, and this will just work. We won't have any issues crashing. Okay. Now removing front. Again, it's going to crash if we're empty. It might be okay because I mean you can't take something away from an empty node. We might want a better logic error if we're empty. We could do something like that. Because we know we're not empty if you're not first or last, right? So I guess we could do that. And if we're going to do it twice, right, removing the back, removing the front, might as well be a helper method, right? We can have a void check for empty. And if my number of items is equal to 0, I'm going to throw a logic error. And or list is empty. Sure. So we can have a quick check for empty here. Does that make sense? So they're not trying to remove something from an empty list here. If it's not 0, I mean, this could crash too. That's a little ugly, I guess. So maybe we might as well check for that. Check for empty. And then we probably also need to check to make sure the index is valid. Index is greater than or equal to my number of items, or my index is less than 0. Right? If you give me a bad index, okay, sure, we can do that. So we can throw a logic error. Logic error. Invalid index. Okay, this is good. Right? We want to make sure we don't do bad things because it will still crash, but we don't want it to crash the wrong way. So yes, I have no idea what that is. Sorry. All right. So we check for empty. Check for empty. You want to do the front or the back first? The front first. Okay. So to remove the front node, then we're going to take the data from the front, right? So our T data is going to equal my first's data. So I've got that. At the end, we're going to return that data when we're done. And we'll probably take our number of items minus minus here. So everything else then. So to skip over the front node now, we need to take the front's next value and change its previous. So first's next value, previous value, is equal to a null pointer. We're out of the list. That's it. Now, this does get tricky though if we only have one item. Right? If we only have one item, do I have a next? No. So we need other special handling. This is why this is crazy. There's like all these different edge cases that can happen where if I'm in a particular shape, bad stuff happens. So this is if my number of items is greater than 1, essentially. Right? We can do that. If I only have one item, then it's no good. Right? Maybe it's easier to say, hey, if it equals 1 first, and we'll do that one case here. And we'll make that the else. I don't know. Is that nicer? It doesn't really matter one way or the other. So if we only have one item here, that's fine. To take ourselves out, we say, hey, first or we're going to have to delete this node. One sec. So we need the current node t node t pointer current is first. Right? We've got the data, and then we'll say my first is equal to a null pointer. My last is equal to a null pointer. Right? And then we can delete the current node. We can return the data. Right? If we only have the one thing, first and last become null now that they're gone. We took away the one thing, we're an empty list again. We need to make sure these are properly nulled, because the rest of my code depends on these being null or not. Right? If we don't link those properly, we're going to be in big trouble. So null them out because we're empty. Right? If first and last are null, it means we're an empty list. I guess probably we can wait because this will still return the data and delete my number of items. Okay, that ought to work okay. So if we're not a single item node though, we just take ourselves out. Say, hey, the thing that comes after me, great. We still need to delete this current node, right? And then we need to repoint first. So if the current node is the first, right? And then first is going to change to become first's next, right? I have a new first. Repoint first. So this is the jump over the old first. So it is save the node to delete it, and then reset first. Or move first, right? Move first. Then we can delete the current node, take our number of items down by 1, return the data. Right? I think that's the two cases. So if we have more than one item, right, last just stays alone, it's perfectly fine. If we had two items, last was pointed at the second item, first was pointed at the first one, first now points to last, and we're okay. Right? Perfectly fine. So same for moving from the back here, just a little different. So this will be our last's data. If we only have one item, well, first and last are the same, right? It's the exact same thing here. We don't care. Well, if we only have one item, we could pretty much remove from front too if we wanted to save a little time here, right? Not have the same code twice. Sure. So if we only have one item, we can say let's return remove front to avoid that special handling twice. Right? If we already have the code, I don't want to repeat myself. If you have the same code twice, you should feel bad about yourself. That's our good rule of thumb. Okay? I joke about it a lot, and it's mostly a joke, but it's a good philosophy. Is that the right term for that? Ideology. Good idea, good ideology. Yeah. Okay. So if we're not there, then so now we're going to take our lasts, previous, next. Right? The thing that came before the last, its next is now null. You now are the last thing. Your next is null. Take our last node, so we can delete it here. Take our last and set it to the last's previous. Delete the current. Take the number of items down by 1. Remove the data. Okay. Now we haven't tried any of this yet. I'm a little worried because we've written a lot of code without trying it. So we should try it, right? Any code that's worth writing is worth testing. We could do unit tests. That's a really nice thing to do. I could just write some in main as well. I feel like sometimes when I write unit tests, it confuses people more, and you'd rather just see it in main. Is that an okay assumption? Okay, so we'll just do it in main. Understanding a unit test is better, but we're just going to play with it for now. Okay, so I'm going to include my doubly linked list here. We should add a bunch of values to it, right? Do you want to add random values or add specific? We could probably add specific values so we know what the order is, right? So let's make a doubly linked list. We'll call it my list here. Yeah, type, you want to do integers? Type int. Okay, take our list. Now, do you want to add? Do you want to add to the front? Do you want to add? Do we still have an add? Did I leave an add method in here? Oh, that's added an index. Oh my goodness. I'm confusing myself here with these overloads. Okay. Do you want to add an index, add to the back, add to the front? What do you want to do? Oh, this check for empty should be private. That's in the wrong spot here. Where did that go? Check for empty should be a private method. No one else needs to do that and throw errors here. Should we call this add at, just so it's less confusing? Or is the overload okay? Call it at. Okay, I like that because that makes more sense to me. All right, so list dot, what do we want to do? Add to the front? Okay, what do we want to add to the front? What value? 12, okay. What's next? List dot, what do you want to do? Add to the back? Okay, what do we want to add to the back? 16, okay. What next? Add what? Add at, okay, where do you want to, what index do you want to put it at? And what data and what index? Add a 4 to what index? What? Well, we don't have an index 15, so that probably won't work.
Oh, so the data first?
Yeah, so
Yeah, so
you want 15, become index 1. You're trying to make a sort, so there'll be 12, 15, 16? Okay, we can do that. So we should have 12 at the front, 16 to the back, and we add an index 1, it becomes the new index 1. So we should have 12, 15, 16, right? Okay, now we can't even print this, right? We should probably add that print method. Now, it's a little ugly to print inside of a class, and that's okay. I'm just going to feel a little bad about it, but not worry too much. So we can include our IO stream. So where do we have a current is not null? We had one of those in here, right? This one. We want this. Right? Essentially, as long as we're not null, we want to see out the current nodes data and maybe an end line. I don't know. Sure. Right? And then go to the next one. Start at 0. I don't even really care about the index value here either, right? Because we're not going for a particular index. It's just start at the first. As long as we're not a null pointer, print it out, keep going. Print it out, keep going. Print it out, keep going. Once you hit a null pointer, game over. So we should be able to call print then, right? List.print and see what we get. Should we try it? I'm crossing my fingers here. We wrote a lot of code. Oh, build errors. Oh, goodness. Singly linked missing type specifier does not support a default int. What did I do wrong here? It's only in singly linked lists. Is that really? That was it? All right, hang on. No, still upset here. Oh, doubly linked list. I didn't rename that one. Our constructor, that's right. So then our last needs to be a null pointer, right, in our constructor. Let's try that. Hey, all right, so fix our constructor to match the name of the class. That makes a lot of sense, right? It's useful. Okay, think it built this time. 12:15, kind of worked. I'm a little bit amazed. We spent a lot of time writing code here, like it's been almost an hour, and it worked. You might say it's okay because I've done it before, but it happens all the time. Like you still screw stuff up. So, I mean, just write an English paper and realize how many mistakes you have in your English paper. It's a very humbling experience, especially when it's like a 20-page essay. Like there's so many errors in 20 pages. It's embarrassing. But it's okay. It happens to everyone. That's why we have proofreaders, right? That's why when you write code in the professional environment, you don't push to production on a Friday. Okay? That is the rule that everyone should follow, even if you're Scott Hanselman and you're fancy and you push to production 8 times on a Friday, it's because he's just bragging. He can do that because he's amazing. But you don't push to production, don't change your production code on a Friday. Leads to bad weekends. Okay, was good? What else should we try? We haven't done everything yet. We haven't removed things. You haven't added lots of things. We could add more. What do you want to try next? List dot. Remove. All right, you want to remove at an index, remove the back, remove the front. Should this be remove at? I feel like that should be remove at now. So where's my little shortcut menu? Do I not have that shortcut menu? I hate this. Remove at. I like that. So remove at what index? Index 2. Okay, that should be the same as removing back. That should remove the 16. And then print it again. We should just get 12 and 15. Oh, uh-oh. Crashed. If index is 0. How do we crash here? It's a weird place to crash. Remove at line 139. Logic error at memory location. What did we even... I'm confused now. Oh, we're at print is where. Wait. Print crashed? That's a weird stack trace. Hang on. Let's try that again. Let's put a breakpoint in here. Run it in debug. Let's step into our function. Did you guys spend enough time with the debugger last semester? I'm assuming everyone knows how to use the debugger, and then I get interesting questions from folks. Which questions are good? I'm happy to have the questions, but when they ask me how to use the debugger, I get confused. So we'll spend more time with it, right? You put a breakpoint in, click the line number right next to the line number, it pauses there. You can step into, step over, step out. Okay, so we stepped into our function remove at. We're going to check for empty. We're fine, we're not empty. Check our number of items. Wow, we got a lot of stuff here. Okay, if the index is greater than or equal to the number of items. Oh, that was a logic error. Why do we only have 2 items? What happened here? We shouldn't have 2 items, right? The add front, add back, and add at. So one of those didn't increase our number of items, right? Does that make sense? Okay, so let's take a look at our add methods here. This is what some people like alphabetize them or do other things, and I put them all over the place because I'm nuts. So add at is not increasing our number of items. That hopefully will fix our issue. Right? Did you see where that broke before when we went remove at? And it said, hey, remove at. Oh my goodness, was about to check that line right here. I said my number of items was 2. Right? If you hover over these, so in debug mode, and you hover over the value, so I'm going to step into the function. So I want to see what this function is doing. Oh, cancel, stop, 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 rerun. Okay, now we'll step in. Stop. All right, it's real confused. That's super weird. Let me just clean and rebuild. Build solution. Okay, it built. Run it. Okay. It gets real weird if you change code places. It didn't successfully recompile it. I don't know why it didn't, but sure. So like clean will like clear everything out and then rebuild it from scratch. So we're at remove at. We said, hey, I want to remove index value of 2. So if you just hover over it, it shows you here, or kind of in your locals window here, what your values are. And then we could see, hey, my number of items, so if I just hovered over it, before was 2, now it's 3. It's super tiny, that's why. You can't really see that, I'm sorry. It's right in front of my face, so I can see it. Obviously, if I can see it, you can see it. Sorry, we'll get there. We'll get there. So now I see, okay, 2 is not greater than or equal to 3. Life is good. We're not going to throw this logic error of an invalid index. Okay, index is not 0. Index, is it equal to number of items minus 1? Yes, it is. Let's remove back. So we'll step into remove back. Check for empty, or not empty. Take our last data, right? So we have this piece of data we're storing here. My number of items is not 1, so we don't have to do any special handling. So we're going to set the last previous. So I can open up this here, and I can open up first and last and see what the next and previous values are. And you can go all the way down the chain here. And if I start at first and go to first next and go to first next next and first next next next, well, that one's null because it's right at the end. But you can explore your linked list in this debug view as far as you want to click. Right? If you've got 1,000 nodes here, you probably actually can't physically see 1,000 in here because they like keep going further and further to the right. But Right? You can look at the values here, and that's the value of the debugger. We can see what is actually being stored where. We'll get current, so we can go delete it. Now we're going to change our last previous. So this last previous value here, right, currently points at this one. Now we're going to change the value of last to be what my previous one is. Now last has changed to point at this node here, right? Okay, cool. We'll delete the current node, take our number of items down one, return the data. Return the data. Print ourselves out, and it'll just continue, run to the end. Oh, I didn't see the output. Shoot. I forgot to look at that window. But now we get 12 and 15. That's good so far. We probably, when we print here, should check for empty as well, because this will just, I guess it won't do anything because we are null pointer, so the while loop will never run. So I guess that's safe. Right, so if we take our list, we want to remove front, and then we want to print, right? We should be left with just the 15 there, right? Now, do you want to remove at? Do you want to remove front? Do you want to remove back? I mean, they all should do the exact same code because that's how we wrote it, which was smart on our part, right, to avoid redundant code. Because if you have a bug in one of those and you have it 3 different times, you have to fix it 3 different times. And if you forget to fix it in one of those 3 different times, you still have the same bug. And that's a bad feeling, right? Thinking you fixed a bug and you didn't actually fix it everywhere. Remember, just remove at 0. And then list print shouldn't really do anything here, right? It should just, they say it's a no operation. We'll say nope, 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 no op. People say weird things all the time. Nothing happens, right? Because that while loop has nothing to do. We started at a null pointer, we're done. How you folks feeling so far? Doubly linked lists are fun. Really cool. Now, we haven't gained a whole lot, but now we're setting ourselves up. We're setting the stage for that positional doubly linked list. So I can say, hey, here's the position where you're in. Now you can add before and after a position in constant time. We don't have time to do that today because we are running short on time. I'm trying to pay attention here. But if we had a position we could give to someone, they could hold on to that position and add before and after in constant time, which is really, really fast in a large set of data, which is really cool. Right? So depending on what the data that we're doing, how we're going to interact with it, right? It can help inform our choices for, hey, does it make sense to use a vector? I know I was really big on vectors and said, just always use a vector. Well, no, it's not always a vector, despite us just liking vectors a lot because they're easy, right? They don't always perform like we want them to. So if I were to go through and try and do a lot of different inserts, vector is probably a bad choice for that because it's going to be slow on a large set of data, right? If I'm only ever adding to the back and I want to read my data at given indexes, that's the great choice because reads are super fast. I can just jump to an index and read it. With a linked list, if you're reading a bunch of data, not in some sort of sequential fashion, just like jumping here and then there and then the front and the back around, that's going to be really slow because you have to do n reads to get to that value there. So a lot of it just depends on how we're going to be using our data. So understanding the problem that we're solving is really important because we have to know like what is happening here with the data we're storing to figure this all out. Okay. The last thing I want to do here, because we've got time for this, is I want to show you a better doubly linked list here. Still not positional, but better. Okay. So let me take all of this here. We're going to add a new header. Make sure I pick the header file this time. This is a circular doubly linked list. And what I like about these, I copied the wrong code. Nope, I want this code here. Is we get to avoid all of the special case handling by doing a trick. So the trick here is I'm going to start with a node here that is explicitly null. So this is like the start, essentially. When I start, its next is itself. Its previous is also itself. So I have a node that will exist. That way I never have a null pointer node. So instead of having a first and having a last, and then the first's previous is null and the last's next is null, I never have that. I have this start, or some people call it the dummy node, or anything you want to call it really. So if I want to add to the front here, well, the starts next here, so starts next is always the first thing. And the starts previous is always the last thing. Because I'm going to have a node that exists just to make sure I have a node in the chain here, and I can always set a next, I can always set a previous. So if I want to add to the front, right, the next value of start is always the front thing. Right, so I'm going to add it in between right here. Right, so to add something in between, I'm going to add a new node here. This will be, at value 1 or something. So that same idea, when we add between things, its previous is now the start node. Its next is whatever this next used to be, right? My next now is this one. And then I say, hey, my previous, your next is me. And then I say, hey, my next, your previous is me. Break this link here and say, you now point to me, right? We put ourselves in the chain. Same with adding the back, same with adding anywhere in the middle, but it removes that special null case handling because I'm always going to have a node here. So I don't need a next and previous, I just have the start. Nope, sorry. So the node has next and previous, sorry. But the class itself, this is the circular doubly linked list. Circular doubly linked list doesn't need a last and first. It just needs a start node here. And when we create it here, the start is going to equal a new node of type T given null data. It has no data. Right? It doesn't need to store anything here. There's just no T value. And then its next, again, it's going to start as a null pointer. And its previous will start as a null pointer. I'm going to go change it. So I can say starts next is the start, and starts previous is the start. So it hooks up the circle here. So what happens is once I have enough nodes in the chain here, I have a circle. So here's my 1. If I want to add in a 2 here, right, I'm going to add that. We'll say add to last. So we'll say, hey, last, you don't point here anymore. Last, you point to here. And if I'm going to add something in, hey, last, the last value, your next thing needs to be this starting node. It's the dummy. You're at the end of the chain here. And what comes before you is what used to come before, right? Which is this one here. And then what comes before me, I now come after you. Break this link here. I come after you. Right? And now I can follow this chain in a circle. It's a circular list here. When I start at start. When I come back to start, I'm done. But this way I always have nodes, which is really handy. So to add to the front, I don't need any sort of special handling. Right? I say, hey, my new node, right? You have the data. Your next value is not first because I don't have a first anymore, but your next value is the starts next, right? And what comes before you is start, right? And then I don't care if I'm the last or not because I always have the start node. I don't need to do any special, there's no first and last to have to set here. I just use that start node because its next is the first thing and its previous is the last thing, always. So add to the back, again, we don't even care here. We don't have to do any special handling here. We just say, sure, if I'm the last thing, what comes after me is start, and what comes before me is starts previous, right? The previous last thing. I don't need to do anything here. Goodness, where's my format button? Why advanced format? Format document. Control E and D. There we go. Control E D. Okay. So you see, it simplifies my add to front, add to back. It just works here. Now, removing back, again, we don't really care too much here. Now, we're never going to use null pointers either. Right? I don't have a last pointer either. So removing from the back and checking for empty is probably still good here. But we can just take the last thing. Let's see, so if we're empty, I guess if we have one item, yeah, one item, we're still fine. So if we're not empty, we're good here. So we'll take our data. We're going to take, well, the back thing is my starts previous data. Right? Starts previous is the last. That's the new last thing. Right? If I'm going to jump it out of the chain here, then I'm going to take my starts previous value and I need to change its next and change its previous. Right? We're just taking it out of the loop here. So the previous value to that one then is going to equal what comes after me. Starts previous next. No, I'm sorry. So my previous is next value. This is okay. It's a little messy. It does. I'm sorry. So the thing that comes before me, what comes after it, is what comes after me. Which, if I'm the last thing, should just be start. Right? So it starts previous next is always the start, because it's the last node in the chain. Right? And then starts previous, right, shouldn't be the previous anymore. It should be the previous previous. The thing that comes before the thing that comes before. Right? We've taken it out of the loop. I know it's nuts. It's a little nuts here, right? But it works. It works. Now, this here, removing, is actually a little awkward too, right? And it's, you know, it's ugly. We don't really like this a whole lot here. So what we can do is we can have a t remove node, and really this would be a private helper function here. Remove node given a node of type t pointer current. Right, so to remove a node, then I'm going to take, I have the current node, right? I'm going to take the data, the current node's data, right? And I'm going to take the current next previous, set it to the current's previous. So what comes after me, hey, what comes before you, jump over me, go to my previous. Hey, thing that comes before me, previous, the thing that comes after you is what comes after me. And then we can delete the current node and return the data. So anytime we have a node, we can delete it with this steps here because we will never have a null pointer, right? Next will always have a value. Previous will always have a value. We never have those nulls at the beginning and end. We've made life easier for us. So to remove a given node here then, so to remove the back, we're just going to check for empty. We should decrease our number of values too. Take our number of items minus minus. There we go. And then we're going to return my remove node of starts previous. That's it. Right? To remove the front, same thing. We're just going to return starts next. That removes the front. Right? To remove at a given index, again, go find the index. We don't really care about these things here because we don't have any extra special handling. Get to a current node. Once I have the current node, I'm going to return remove node given the current node. Right? So all of my special handling here is going away. The only thing I have here now is walking and a sanity check. Is it a valid index? Get to the current node. Remove that current node. Hey, if it's the front or back, I know it starts next or starts previous. If it's somewhere in the middle, go find it. Go walk to it. Remove that node. And then adding here, right? Add the new node. That's all well and good here. So let's see, we do add back, add front. So we could even take all of this code here and make a private helper. Void add node. Does that make any sense here? Probably not. No, because I don't think we're really saving. We would save like the number of items plus plus. Doesn't really save a whole lot of code. I guess it does. That's fine. So we'll have a void add between given t data the node of type t pointer. I'm going to say previous and the node of type t pointer next. And we should flip those around, right? Because they're in the other order otherwise. If you give me the next and the previous, we'll take a node, make a new node here. Its next is the next. Its previous is the previous. Increase the number of items. That's it, right? So to add to the front, then we're going to add between the data. What comes next is starts next. What comes before is just start. Right? Same with this one here. What comes, if we're adding to the back, what comes next is start. Right? Because the last thing circles back to start, and what comes before that is starts previous. So to add at a given index, then, once we get to a current node, right, we don't need to do any of this other stuff here. We can just add between. Well, if we want to be at that index, what comes next is the current node. What comes before us is the current node's previous. Right? Does this look a whole lot cleaner? That's what circular doubly linked lists are amazing. They're like the cleanest thing because we have removed all those edge cases. I always have the start. Now the last thing we need to do is we're never going to get to a null pointer. So a current node does not equal start is the important catch here. Because once we get back to the start, now we're in trouble here. And we don't have a first, we have starts next. Right? We don't have a first, we have starts next. We go until we hit start. So I think that's all of them here. Oh, I'm sorry, we ran out of time. I was not even looking. You guys got to yell at me. I'm sorry. I'm just going to keep talking. I got my coffee. I'm writing code. I'm happy. I'll see you folks on Wednesday. Thank you so much. Sorry about that. Thanks for hanging online, folks. Good to see you.